we're going to take the number of groups of protons and carbons that we see when we look at a structure and figure out what the basic appearance of the number of groups in the NMR spectrum will look like, up one notch from the methyl ethyl ketone, diethyl ketone example we did a little bit ago, and take it up to some aromatic molecules, because these tend to be areas for students when they're first thinking about this and being reminded of these things, for example, back in their organic chemistry days, find just a little bit, it takes a little bit of work getting used to. So what I want to do is go through and look at some aromatic molecules and examine number of hydrogens in them, number of hydrogen groups, and for these we'll also look at their integrations, number of carbons, and number of carbon groups. Okay? And we're going to go through a series of related aromatic molecules to try to illustrate applying the ideas of distinct hydrogen groups, integrations, distinct carbon groups, and looking at what symmetry does to simplify an NMR spectrum of these types of molecules. And the first one I'm going to look at is chlorobenzene. Okay? There is its classic organic structure that you learned about. Now remember, each of these points has a hydrogen attached to it. Here is the chlorine. Then, there's alternating single double bonds, the classic organic structure. We look at a structure like this, and we're going to note first, 1, 2, 3, 4, there are 5 hydrogens in there, okay? Whether it's symmetric or not, there are 5 hydrogens in this thing. But we do look at this thing and we do note that it is symmetric. Particularly, I'm going to draw kind of this dashed line to represent the mirror plane here, that these two hydrogens are on opposite sides of a mirror plane. And as we saw in a couple of our earlier examples, hydrogens on opposite side of a mirror plane will form one group in an NMR spectrum, not two. There are a couple of unusual exceptions to that we will get in detail later, but for right now we are doing the kind of the basic analysis here, and what we will see is the ortho position hydrogens here will form one group. The meta position hydrogens, they are farther from the chlorine, so they are a distinct group, but they will form, the two hydrogens will form one group. And then finally the para position forms its own group. So there are 3 groups, distinct hydrogen groups in here, and one of them in a 2 to 2 to 1 ratio. Now, if you write that 2 to 2 to 1, 1 to 2 to 2, or whatever, who cares? But those are the general ratios. Now, remember, ideally, a proton NMR spectrum now will show in the aromatic region 3 groups integrating in a beautiful 2 to 2 to 1 ratio. In reality, it may look like that. Some of this, because it's a proton spectrum, can be compressed and somewhat overlapped. So this would be the ideal scenario. Now we turn our attention to the carbons, and this molecule has 6 carbons in there, but the plane of symmetry that works for the hydrogens also works here. These 2 carbons, the ortho carbons, are one group. The 2 meta carbons are one group. The para position is its own group. And then there's this dude up here. Now, we didn't look at that position before because there's no hydrogen there. But there is a carbon. A lot of times students, when they're first doing this, will overlook that one. So there is a 4th carbon group in here. Technically, it's called the ipso position, where the substituent attaches to the aromatic ring. So there are 4 carbon groups. 1, 2, 3, 4. Remember, for very good reasons that we aren't going to talk about right now, we don't integrate proton spectra, so I don't have any integrations for it, but that's how we would analyze this particular molecule. So now I'm going to apply the magic eraser, and we're going to look at the next one in this series. Now, the next one I want to look at is a close relative. It's going to be this one, the orthodichlorobenzene. So, same basic structure here. Now we've got 2 chlorines on it. Looking at the number of protons, there are 1, 2, 3, 4 of them. Okay, so there are 4, but we look for, potentially 4 groups or less. This one is symmetric, and it is sometimes a good idea, especially when you're getting used to doing this, to kind of note where that symmetry plane is. The left side and the right side of this molecule are symmetric. That's going to mean these 2 protons form one group. These 2 protons are going to form one group, and that's it. So we're going to have 2 groups, and they're going to technically have a 2 to 2, although if we reduce it to the smallest whole numbers, 1 to 1 ratio. And again, ideally, there would be 2 distinct resonances in the aromatic region of the NMR spectrum. In reality, they could overlap. There could be other complications going on, but that is at least the first line and first pass at analyzing this thing. For the carbons, it's an aromatic molecule. It still has the 6 carbons, but looking at it here, these 2, of course, if the protons were symmetric and formed one group, so will the carbons. A second set of carbons, and then of course these, there are 3 distinct groups here. All right, so onto the magic eraser, and let's take a look at the next one. The next one, no surprise, it's going to be the meta-dichlorobenzene. I'm going to draw that structure here. Remember meta, where they're in this position here. Now, analyzing it again for a moment, we have the 1, 2, 3, 4 protons in there. That hasn't changed. But looking at it, sometimes students, if you're not careful, will not recognize that there is a plane of symmetry here. We sometimes get kind of biased to think the plane of symmetry must always be up and down, and we often will orient our molecule to have that, but it's not necessary for there to be a plane of symmetry, that it be in the vertical position. There is one here, and it's there. Okay, it's sometimes students, when they're starting out, have a hard time finding it sometimes in a structure like this. Now, it is true, I could have drawn it with this configuration where the mirror plane is vertical. But let's face it, you're not always going to get, the structure drawn in the most easy to look at, ideal configuration. Sometimes it's going to be drawn however it's drawn. So you have to kind of learn to deal with it here. So looking at the number of groups, there is only actually one group on opposite sides of the mirror plane. So there's going to be one group there, a second group, and a third group. And these 2, remember, are not one group, are not related by symmetry. The mirror plane is here, but this side, these 2 sides of the molecule are not symmetric. So we're going to have 3 distinct groups in this one with a 2 to 1 to 1 ratio. And I'll finally point out 2 and 1, sure enough, do add up to 4, the total number of hydrogens in here. Looking at the number of carbons, same type of molecule we've been looking at, it has 6 carbons, but 1, 2, 3, 4. There are 4 distinct carbon groups in this thing. All right, no great surprise what the last one's going to be. One more application of the magic eraser, and on to the next. Surprise! This one is the para configuration, ParaDichlorobenzene. Okay, there it is. So there's the lovely structure of it here, and sure enough, it has the standard 4 hydrogens that we've seen in some of the other examples. Yes, it has a lovely mirror plane right here, but do you see there's another one right there? The top and bottom and left and right of this thing are symmetric. This is a highly symmetric structure here. So that is going to render, the vertical mirror plane renders these 2 equivalent to each other. The horizontal mirror plane renders these 2 equivalent to each other. If these are equivalent to each other, those are equivalent to each other, then let's face it, those are equivalent to each other, these are equivalent to each other. Realize we have 1 proton group in this thing. So we're going to get just 1 peak. It will integrate to 1. We know it represents 4, so we would have an extraordinarily simple NMR spectrum for this particular molecule here. Looking at the carbons, the same symmetries are going to apply. There are a total of 6, but these two equivalent, these two equivalent, these are equivalent. So all 4 of these are equivalent, but the 2 carbons that where the chlorines attach, they are not equivalent to the carbons where the hydrogens are attached. That wouldn't be true, but this mirror plane renders this one and that one equivalent. So there are only 2 carbon groups in this thing. All right. So keep that in mind when you're looking at these structures. The aromatics, they are often, by themselves, even in a large molecule, the aromatic ring carries along its own bit of symmetry that plays a role in determining the number of distinct groups for protons and carbons. So keep that in mind, practice a few more, and we'll talk to you later.